All right, I think it's working. Yep. Hold on a second. I don't remember if I ever set the Zoom. If I don't do that, it'll get fuzzy. We're good. Okay, so I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for these students. Just ask you just guide our steps today. Help us to understand more about your creation, and just the students would ask good questions as they think of them, Lord. In your name I pray, Lord Jesus. Amen. So I defined, F holomorphic on domain D means what? F prime of z naught equal to the limit as z goes to z naught of f of z minus f of z naught over z minus z naught exists, right? For each z naught and d. Now, just reminder, what is this? This is a loaded word here. What's this mean? Domain. What is that? We had a definition for a domain in here, topologically. That means something. No one knows? Yeah?
Open set.
Open set. I got open. What, you got anything to add that, Ben?
Yes.
Yeah, open connected set. That's right. Open connected. So
The just connected, not like path connected.
connected implies path connected here, vice versa.
Oh, right.
Yeah. Path connected is connected in our current context. So anyway, well, for an open set. So anyway, open connected set's a domain, and so holomorphic means that it's complex differentiable at each point in the domain, right? And I'm sorry, I seem to have written the limit of the difference quotient again. My bad. I was trying not to do that, but just to make sure you understand, that's like what's at the base of everything, right? But we had a theorem which was beautiful, and the theorem said this. It says that f equals to u plus iv, continuously differentiable on domain D. All right, then f holomorphic on D if and only if, well, partial f partial y is equal to I times partial f partial x. All right. These right here are the Cauchy-Riemann equations. So if the Cauchy-Riemann equations hold on a open connected set for a continuously differentiable function, it's holomorphic. All right? We'd like to understand better, like, what is this structure actually giving us? Okay, that's what we're going to try to examine today. Please understand that continuously differentiable, I'm talking about the continuity of the real partial derivatives of the component functions here, the u and the v, with respect to x and y. All right? And I'm assuming that, like, ux and uy, vx and vy, these are all continuous functions on the domain. That's what I mean by continuously differentiable, like we just introduced like last week, right? Okay, so anyway, any questions? Yeah.
Because differentiable doesn't imply continuous, and also continuous doesn't imply differentiable.
Well, differentiable does imply continuous, but it doesn't imply, but you can have a function in the real sense which is differentiable, and yet the derivative itself is not continuous. So differentiability implies continuity of the function, but that is not necessarily tied to continuity of the derivative of the function.
Okay. So when we're saying
In the real case.
differentiable, we're also saying the derivative has to be continuous too.
That's what that means. Continuously differentiable means the derivative is continuous. Otherwise, it'd be, yeah.
Good to clarify.
So, like, one of the homework problems, of course, is given that a function is complex differentiable, show that that implies that the function is continuous, So that's like one of your homework problems. That's a Calculus 1 problem, right? That should be like in the first 2 months of Calc 1, you should prove that. Anyway, so listen, when I say Cauchy-Riemann equations, I don't always think this. You might call these the vector Cauchy-Riemann equations, right? So what does this mean? Like, let's not be mysterious. Whoa, I can do that again if I tried. Let's see here. So uy plus I vy, that's what this is, right? And what is this? This is I ux plus I vx. That's how we define those partial derivatives, right? Component-wise. And so if you multiply this out, get yourself I ux minus vx, right? So in order for those to be equal, that tells us two, scalar Cauchy-Riemann equations. Namely, what do we have here? The real part has to be equal to the real part. So this has to match that. So what you got yourself is a uy equals to minus vx. And we also, of course, have vy equals to ux. So there you go. Oftentimes, these or minus these are referred to as the Cauchy-Riemann equations. So when I talk about Cauchy-Riemann equations, you should understand that I freely go back and forth between this and this. And when it suits me, the Wertinger. I should say it with a proper German accent. There we go. I used to have a friend from India, and for fun I'd be like, Tapomoy, would you say windshield wiper for me? He'd be like, shut up, you're a bad man. I'd be like, no, say it for me. He'd be like, fine, windshield viper. I'd be like, thank you, Tapomoy. I wonder where Tapomoy is now. He's a fascinating fellow. He went to like elite schools in general relativity in India, and he knew things in the course when I took it with him in graduate school in physics. He knew things. Like, he was like, we'd go through this derivation, and I was like, huh, that's neat. And he'd be like, no, you don't understand. In my previous coursework, that was 3 pages. He just did 3 pages of index calculations in like a third of a page. It wasn't just good, that was masterful. You don't understand how good he is at what he's doing. I'm like, no, I don't. But I'm really happy to have you as a classmate, like, wow, perspective. But anyway, he ended up transferring to another school, and then, as I understand it, he left physics to study photography. So,
No.
So I don't know.
Legendary.
Okay, so
Look at MCF.
So theorem, if f equals to, oh, by the way, notation. F holomorphic on D, we have notation for this. This means f is an element of funny looking circle D. It's like a cursive O. So that's the set of all holomorphic functions on D. All right, so if f is an element of the holomorphic functions on D, and well, then Naritonia, then it is. There's
a Maki.
It's huh. That's not on purpose, but I like it. That's a standard notation that exists outside my realm.
It's weird.
Yeah.
What's he called?
Well, he's saying it looks like a symbol from Naruto.
Yeah, but
And
what's it actually called?
I don't know. I mean, it's like a script O. I'm not.
Script fancy.
Script fancy O. Well, there you go. That's the technical name right there. So, I mean, if you want to know how I tech it, it's mathcal O. Anyway, so f is holomorphic on a domain D, then fxx plus fyy is equal to 0. All right. Oh, man. All right, guys. My apologies. I'll eventually get rid of this cough. Well, yeah, we'll see. Okay, so proof. if f is an element of the holomorphic functions on D, then we know we have the Cauchy-Riemann equations, namely fx is equal to ify. Excuse me, is that right? My bad. Fy is equal to ifx, right? So, oh, I'm sorry. I should say, I need some preamble here. Given our current technology, I should say we're, come on. Man, it's really on there. Let's presuppose f smooth. All right, in the sense that it has, you can take as many partial derivatives as you want. All right, smooth function in the real sense. We'll eventually learn that we get that for free. If f is holomorphic on D, it's necessarily smooth. But that's later. We don't have the technology for that yet. So we have to make the assumption at the moment. OK? So fine. Then what? Well, see, that's, I realized I need that at this point, because if I differentiate this with respect to x, what do I get? But we can do what? We can pull the I out, right? And then we have partial x fx, also known as I xx. I mean, why use one notation when you can use two, right? Or three. I guess I've got three partial derivative notations going on right now on the board, don't I? I got the fraction notation, the subscript notation, the operator. It's all going. OK, anyway, so there's that. Then what? Well, on the other hand, I could partial differentiate with respect to y, right? And partial y, fy, would be equal to what? Partial y of I fx, which would be I partial y fx, right? Which would, of course, we could write that as I f. Well, let me just say that. Fine. So look at this then. We have partial x of fy is equal to partial y of fx, right? Of fx, right? Because the partial derivatives commute. So on the one hand, I can write that this is I fx, right? On the other hand, take this equation here and do what? Divide I to the other side, right? So minus I fyy equals to partial y fx. You see that? So putting that over here, I have minus I fyy, which then implies f of x plus fyy is equal to 0. Now, listen, guys. It probably looks more complicated than it actually is, because my brain is not quite right today. This, you can, listen, don't follow my derivation here. Find your own. It's really easy. OK? Like, let's try it again. Let's try it again. I'll do it at the component level. Here's uxx plus uyy, right? So that's ux, the x derivative, plus uy, the y derivative, right? So at the component level, what's ux? Well, ux is equal to dy. And uy is equal to minus vx, right? And then this gives me vxy minus vyx. That's the way that notation works. The subscript you're differentiating goes, yeah, it's weird, but anyway. Of course, those are equal, so it's 0. Yay! Now, definition. I think I told you guys this last time, but if a function solves this, it's said to be harmonic, right? So another way to say this theorem is that if you have a function which is holomorphic on a domain, that implies that it's harmonic on the domain. But that also means that the real part and the imaginary part of the function are separately harmonic functions. They're solutions to to Laplace's equation. Any questions? Let's look at an example here. Man, go for it.
What's the Laplace equation?
Laplace equation is the one that's on the board. It's the
F double x plus F double
yeah,
equals 0.
yeah.
Okay.
But I usually change the letter just so it's not like, I don't know, like here now Laplace's equation, phi xx plus phi yy equal to 0, or this partial x squared plus partial y squared acting on phi equals to 0. Sometimes I like that. All right, let me work an example here, yeah? So example 1, what if we had, let's look at the log of x, log of z rather, right? So that's the natural log of the modulus of z plus I times arg z, all right? Are you guys with me? Okay, so what does this theorem I just wrote down mean? Now where, we defined this for what? For z in the punctured plane, right? So the plane with the origin punched out is the punctured plane. So, is that a domain? Well, yeah, it is. It is domain. Is this function continuously differentiable on that domain? I think it is, actually.
In the domain.
Yeah. Does it satisfy the Cauchy-Riemann equations? Sorry, there's something I'm not saying at the moment. It's bothering me. Let's go on here. It'll come to me. So this is 1/2 natural log x squared plus y squared. See, continuous differentiability is a local property. So, I don't, actually I think that's not, well, sorry, I'm forgetting something to say here. Now I could say this is I times inverse tangent of like y over x, but this now, I've added a term and condition here. Now I'm for z, you know, the real part of z positive, right? That's what the principal argument is there. And yes, sir?
Could you sort of clarify what local property means versus, I guess the opposite would be like global property, right?
We'll get there. Yeah, it has to happen organically. I can't do that now.
So long as we got that.
Yeah. But I mean, I can tell you this. Like local means it's something I can say about at a point. So continuous differentiability, I'm talking about at that point, there exists an open set on which the partial derivatives, you know, are continuous. That's continuous differentiability at a point. Holomorphic at a point, also with a local concept. At that point, there exists an open set on which the function is complex differentiable. Global, I think, is what it kind of sounds like. But that's not, the reason I say I haven't answered it yet is there's something else here that I haven't, anyway. Okay, so on the positive half plane, there's your component functions, right? Now, is this a complex differentiable map? I mean, is this a holomorphic map on the half plane? What do you guys think? I know I don't want to do the difference quotient, right? I'm not entirely sure I really want to do the Cauchy-Riemann equations here either. I'll just say this. Let me just leave it as an exercise for you guys, an unpleasant one, but not impossible. You can show that ux is equal to vy. You can show that uy is equal to minus vx. In fact, those equations are true. It checks. This is, in fact, a complex. This is a holomorphic function. Yeah.
Isn't that kind of what we've been doing in the homework in the last mission? Because like a lot of times we would find a partial x and a partial y, and then it would be like the...
That is true. So in retrospect, the patterns that you guys saw in the Jacobian matrix of certain functions, that has actually, in retrospect, evidence that those are complex differentiable functions in view of that theorem. Yeah.
Because we had said that or the Jacobian being complex linear implies they satisfy the Cauchy-Riemann equation, the other way around.
Right. The Jacobian being complex linear is equivalent to the relation between the partial derivative of x and y being what I have written over there, which in other words means that the second column in the Jacobian matrix is obtained from the first by just multiplication by I. Yeah.
I think we did this in a specific example.
Oh, okay. So, but my larger takeaway here at the moment is that then that means that both this and that are solutions to Laplace's equation. So, anyway, the interesting thing though is that log z is not an element of the holomorphic functions on the punctured plane because of the angle degeneracy. See, you have a problem. You have a problem in your homework that you prove that complex differentiable implies continuous, right? So what about log z, if we think about it for a second here? So it's and the principal one. Here's the picture of the domain, right? Well, excuse me. What I'm drawing right now is C minus. So C, and let me just draw the complex plane as if it has an end, just to keep us in the box. All right. So here's the origin. This is C minus. It's the complex plane with the negative real axis removed. What I'm telling you is that it is true that log, and I know this is like mathematically a little bit, not quite right to include the z in the function. Like maybe I should say log without the z, but just as a matter of, I don't know, laziness, I leave the z there. All right, with the understanding I'm talking about the function, not its value. Okay, and it is holomorphic on this thing. That is true. So what's the problem? Why can't you include what happens at the ray? What's the problem? It's because if you study the path limit this way and that way, right? If you study, pick a point and, approach from there and there, right? And if you look at, the log, so what's the formula? Log is, so if this point right here is like, let's say, x naught, right? Z equals to x naught, which is less than 0, right? And if you have x naught plus I delta, right? And you take the argument of that. I mean, put minus there in my color coding, minus I delta. Whereas if you do arg of x naught plus I delta, where I'm thinking of delta as a very, very small positive quantity for the sake of discussion. Think about what happens there. So as delta shrinks to 0, you're always above here. So what's your standard angle? We sweep 0 over to pi. It's pi. What's the standard angle down here? 0 down back to negative pi. And that's the problem. So if I approach, so this proves, if you were to make this formal, you can look at the path limit this way, the path limit that way for the principal logarithm. They're not equal because the imaginary parts don't match. Now the real parts match. There's no trouble at all with the real part, is there? Right? It's not. So, so because of this issue, any choice of argument, it doesn't matter if you, like this one, the principal argument, of course, has the angle jump at here, right? But every choice of argument has an angle jump somewhere. And because of that, the argument will not be a harmonic function on the whole plane. However, what about this? That's got no problem. There's no angle jump problem for this, right? So this actually turns out is harmonic on the whole plane. Which means that you can use the real part of a logarithm to solve Laplace's equation if you want. So anyway, well, all right, let me go on here. I'm spending too much time on that, and I think I'm kind of half doing one of your homework problems, which I try not to do. All right, so, yeah, no, okay. That was just a stretch. That was not a question. All right. There's another way we can understand that the logarithm is complex differentiable, right? Because we define it actually as the inverse function to the exponential, right? So if we had this thing called the inverse function theorem, we can prove that the logarithm exists, and because it's defined as the inverse function of the complex exponential, you know, once we pick it, well, in context, then the inverse function theorem gives us the differentiability of the logarithm. We don't actually even have to, in principle, check the Cauchy-Riemann equations because the existence of the derivative of the logarithm is given to us by the inverse function theorem. That's like a slicker way to do it. That's why I'm not doing those partial derivatives in class. All right, so I should get back to that. But I probably should finish the thought here first, right? So what's the obvious question? The other way, right? Well, that's not quite the other way. The obvious question to ask is, what if you have one holomorphic, what if we have one harmonic function, right? And you want to find another one. Can we do that? Can we find, in other words, let me restate it. Let me state the problem more clearly here. What if we have a harmonic function, all right, on a domain, let's say. So here's the problem. Suppose uxx plus uyy equals to 0 for some smooth, let's just make it smooth to keep it nice, smooth function u on D, and we'll think of D as a domain, all right? Can we find V such that U plus IV is holomorphic on D? In other words, what would that also mean? Excuse me. If we could do that, that would also mean V is what? V is also harmonic, right? On D. Shall we try this? Let's try this. So let's try this calculation out here. Example 2. So let's look at u equal to, I don't know. This should be a fun one. E to the x cosine of y. Is that harmonic? Search your heart. Find it to be true. So we want to find a v such that u plus iv is complex differentiable on D, right? So what is it? So we're looking for basically a smooth function. We'd have u and v both smooth, right? So if they satisfy the Cauchy-Riemann equations, it'd be aces for us, right? I mean, pick your favorite story of happiness. So what do we need to solve? Yeah? We need to solve ux equal to vy. And we need to solve, oh, let me write it the other way. We need to solve vy equal to ux. And we need to solve vx equals to minus uy. Now u is given here, so we can calculate these derivatives. So ux is, well, e to the x cosine y. And minus uy is, well, e to the x sine y. So what do we do when we're up against something like this? We integrate. Integrate with respect to y. Integrate with respect to x, right? If we do that, we have v equals to, what's the integral of this with respect to y? Well, it is e to the x sine y. And then we have to add a constant. But our constant here is not a real constant, right? If we're doing an integration with respect to y while holding x fixed, our constant is in principle a function of x, yes? So we write c1 of x there. And then, okay, so we could do that. If we integrated with respect to x, on the other hand, we get v equals to what? Well, integrating this with respect to x would give me e to the x sine y plus, well, and this time a constant which is a function of y, right? So this is one method you can use to try to find a harmonic conjugate. You just integrate each of the Cauchy-Riemann equations separately, and then you look at them and go, huh, well, looks like I can just make both of these honest-to-goodness constants and see from this that my v should just be e to the x sine y, right? Yay. At least there's a solution, right? We're solving a pair of partial differential equations. So it's good you guys had that class in partial differential equations that we don't offer. I'm just kidding. You did this in Calc 3. Yeah.
Actually, speaking of which, in Calc 3,
So you want me to do this. Partial v partial x is equal to e to the x sine y, right? So I take this and I plug that down in here. And that gives me that partial x. I think this is your question. I could be wrong. Okay, so c1 is equal to what? It's equal to e to the x, where was I? E to the x sine y, right?
yeah.
Which then tells me that partial c1 partial x is equal to what? 0.
Is it a C, sorry? Oh, C1.
My bad. My point is you partial integrate one of them, and then you can take that and plug it into the other Cauchy-Riemann equation. Then that will either tell you that the constant is actually an honest-goodness constant, or it will end up giving you a differential equation which you can solve and then find the function which is supposed to go there. Or when you plug it in, it doesn't work, which is what that means is that, well, there isn't a harmonic conjugate, which would be disconcerting, wouldn't it? If you couldn't find a harmonic conjugate. When can you find a harmonic conjugate? When does this procedure work? Oh, by the way, what did we just figure out? Our u plus iv is what? E to the x cosine y plus I e to the x sine y. What's that?
Well, that's just e to the z.
E to the z, right.
So my question is more from Calc 3, when I had it with Dr. Wang, he had showed us a little heuristic where when you're integrating multivariable functions like that, you take unique terms from each of the results of integration
Yeah.
and put them together almost like a GCD.
Well, that's what I just did here. I didn't put 2 copies of this, right? One will do.
Is there a way, like, is there a justification not like a proof per se, but like some sort of line of reasoning behind that.
Well, you're trying to solve the differential equations, so
I mean, like,
it ultimately
why are you
just
allowed
the
to do that? Why are you?
because it works.
allowed to use that?
Because it works. I mean, if you're solving a differential equation, you're making an educated guess about what function you'll plug back into the equations that will solve it. So if having one copy automatically makes those terms appear, then you don't need two. And so by looking at that sort of, what do you say, common GCD or one of, I mean,
LCM 1 and 0.
one of each.
Yeah.
But anyway, so yeah. But you're right, there's something to think about here, because what is the calculation we're doing really? What are we really trying to do right now? We're trying to find a potential function for a particular vector field, are we not? So you guys remember this? F equals to the gradient of a potential function phi on, on D. This would make what? F conservative. Remember that?
Yeah.
On D. Do you guys remember other equivalent characterizations of conservative vector field? Oh, thanks. You got me.
Took calculus in community college.
Oh, well, we all... What does Dr. Sprano always say? He's like, yeah, we all make decisions. Yep.
Yeah, true. The path integral on any closed loop is 0.
Ah, you wanted to get loopy on me. I'll allow it. The integral around loop of f dot dr is equal to 0. Very good. If and only if what? The integral along c1 of f dot dr is equal to the integral along c2 of f dot dr for coterminal paths, which of course are inside my domain D. I keep drawing it as a rectangle, doesn't have to be. And it's got fuzzy edges, it's a domain. So,
Isn't there a statement about being able to evaluate the integrated function at like any place?
well, once you have that, you have FTC2, so yeah.
Okay.
But let's look at this. So, so this is not in my notes. I just found this like yesterday. So let me write it out for you guys. Given U, we seek V such that Vx equals minus Uy and Vy equals to Ux. If you think about that, we're looking for the vector field formed by Vx comma Vy, which is the gradient of the vector field, gradient of the V function. See, V would be the potential for this vector field, Vx, Vy. Now you're like, well, but you don't know that, that's what you're trying to find, but we do know what we're trying to find because we're given the U. So we're really trying to find F is equal to minus Uy, Ux. In fact, this is given, right? In this whole question, that's a given vector field. So the question is this conservative, right? If it is conservative, if F is conservative, then in fact we can write V of Z is equal to the integral from some point P naught to Z of F dot dr. This is the standard construction. So P naught would be like some point here, some point in your domain. The domain is connected, so P naught can be connected to Z. And it doesn't matter which integral that you're, see this notation makes sense because it's path independent, so it doesn't matter which path you take. And it turns out that this constructs the potential by integration. You use this in physics when you construct the potential from integrating the electric field, for example. Now, specifically, in terms of the line integral notation from calculus 3, this f dot dr is literally minus uy dx plus ux dy, right? So if you want a stone cold formula to calculate the harmonic conjugate, there it is. This lovely formula has wrapped in it everything we just did in example 2. Now, honestly, guys, when I want to find a harmonic conjugate, first thing I do is ask myself the question, which complex function did this stupid professor just take and look at just the real or imaginary component of it? Because that's how I always come up with harmonic functions. I take a complex function that I like and I just pick a real or imaginary part. So if you can see what I did, it's even easier. You can just go, oh, this function is the real part of blah. So it's harmonic, and its harmonic conjugate is this, because you created this with this thing, you know? Here. For those of you who don't understand what I just said, let me show you what I'm talking about. Oh, man. Ugh. All right, so where was I? Example 3, and I'll return to the proof. Just pause for a second. I tell you, oh, I don't know. U is equal to 3 times x squared minus y squared. What should you tell me the harmonic conjugate is to this? If you should recognize, this is what? This is what? This is the real part of what? Complex function.
The complex, or the log of the conjugate?
Mm-mm.
No, yeah, I tried.
Modulus of the conjugate. 3z squared.
Ah, there we go. Yes. 3z squared. So z squared, the real component in z squared is x squared minus y squared. Therefore, since 3z squared is actually equal to 3 times x squared minus y squared plus 6ixy, voila, v equals to 6xy. There's your harmonic conjugate using the theorem that I've just proved. Although I haven't proved this theorem yet. We're getting there. Yep.
Maybe.
I haven't even stated the theorem yet.
Maybe dumb question. Is there any significance to conjugate of z quantity squared?
Not that I know of. I mean, there might be, but I don't know offhand. Here's a deeper question. Where's my phone? It was a deeper question. It was under my notes. So I am also easily amused, so it's good. But let's see here. Where was I? So what I'm trying to describe to you is to find the harmonic conjugate. It's tantamount to finding a potential for a vector field, right? Which we're trying to find this, but what does it take for the vector field to be conservative? Do you guys remember? Well, how about let's be a little bit more topological here for a second. So if D is a simply connected domain, all right, and U harmonic, all right, consider, so let's draw a picture, right? So simply connected basically means that it doesn't have, I mean, it might have some kind of jagged thing bit out of it, and it could even have some kind of missing whatever. I mean, it doesn't have to be that pretty, but the point is it's got no holes in it, in the sense that I can take any loop, right? I can take any loop in the space, right? And I can deform that loop to a point. I never get stuck on anything outside the space. What's not simply connected? How about, what's that?
Washer?
A washer? Very good. Yeah, washer is not simply connected. Very good. Because if I take this loop, I try to deform it, I get stuck on the inner washer, right? How about this one? The punctured plane is actually the big one. Missing the origin, right? So if I have any loop that encircles the origin, if I try to deform it to a point, I get stuck right there. Residue theorem. I don't know what that means, but in time. So, I haven't prepared that far ahead. You've seen Canvas. So, all right. So, see, it's a good thing that I didn't finish the Canvas shell, because if I had, I couldn't have made that joke now. So it was all for the sake of comedy. All right. So simply connected domain. We take any loop you like in here, right? A loop. Take a loop, right? And if we look at the integral of the vector field we're looking at around the loop, right? Let me say that loop is the boundary of this region, this subregion here. I'll call it R. All right, R. Dot dr. Then what can I do? Well, first of all, let me just write out the details. That's the integral around the boundary of R. What was my f? My f was, where was I? Minus uy dx. So minus uy dx plus ux dy, right? Yep. And then what can we do?
If it's conservative, that equals 0.
Oh, yes, if it's this better be, so we'd like to show it's 0. If we could show, to guide the logic, if we could show this is 0 from the data that we have, we'd be golden, because that would have been that the integral around an arbitrary path, an arbitrary loop is 0, therefore it's path independent, therefore I can build the potential from that formula over there, therefore V exists and it's a harmonic conjugate to U. Why is this integral 0? Do you guys remember Green's theorem? What does Green's theorem say? It says this is the double integral over the region. And then what do I do? Remember, this is like the P and this is like the Q. We do what? We do Qx minus Py, right? dA. But what is the Qx and the Qy here? Qx is Uxx. Qy, Py is Uyy, but there's a minus, so we get plus Uyy. Man, it sure would be nice if we had assumed that Uxx plus Uyy was 0. Oh, but we didn't, right? Because it's harmonic. So this is equal to 0. So this proves that if you have a harmonic function on a simply connected domain, there exists a harmonic conjugate. So this will not be futile. This will work out for us. In fact, this is harmonic on the whole complex plane. So this is actually the harmonic. I mean, E to Z is entire. It's a complex differentiable function on all of C. Yes, sir.
Isn't there a equivalent to the fundamental theorem in calculus that is both Green's theorem and Stokes' theorem in 2 dimensions at the same time?
I mean, I suppose this is true, but I mean, yeah.
Hence what?
Yeah, I think you're right. I mean, I use Green's theorem to prove both Stokes' theorem and the divergence theorem in Calc 3. But anyway, this is the, so yes, the grown-up version of this in 3 dimensions, you have a simply connected solid region, you look at a surface in that solid region, you apply the Stokes theorem there, and that allows you to trade the integral around this curve on your surface for the flux integral of the curl over that surface. So if the curl vanishes at an arbitrary point in a 3-dimensional simply connected region, then that implies that the vector field's conservative. But it requires the simple connectedness, because otherwise, when you imagine taking the surface inside the 3-dimensional space, you could get a hole, and if there's a hole, then you can get hung up. You can't apply Stokes' theorem to a surface with a hole unless you're willing to adjust it for, like, subtracting out the middle part and junk like that, which we'll get to eventually. But yeah, residues, yes. Okay, so I think I have spent too much time on this theorem, so I must now project. But any questions? Yep.
So sort of intuitively, we need it to be simply connected because if you're going to do the shrinking part, you need it to actually like work and not map outside the set.
Right, yeah. If it needs to be simply connected, because otherwise, when I make the loop, I might be, if there's a loop and there's a hole in my set, I can't apply Green's theorem there. That's where the proof gets hung up. Yeah?
This is a really broad question. Like, I understand, like, because you jumped in and said, like, we explain complex
Can I erase this, by the way?
functions geometrically with the complex plane, but I don't know why we do that. You know, like it seems like there's an advantage to it. I just don't know what the advantage is.
I don't quite understand your question yet. Could you repeat it?
So I'm just wondering why we describe complex numbers as vectors, or at least similar to vectors.
Because we can. You could do otherwise. You could define complex numbers as 2 by 2 matrices of a particular type, but then pictures of 2-dimensional matrices are harder to draw.
So it just makes doing the math easier, or?
I mean, there's a 1-to-1 correspondence between complex multiplication and rotations and dilations in the plane, so, you know, it just makes sense to look at it that way. So before I get that out, let me just give you guys a really simple low-tech explanation of the inverse function theorem. Do you guys know what the inverse function theorem is? So, theorem, if you have f is a mapping from like Rn to Rn, all right? And the Jacobian of f at a point exists, all right? So let's suppose that this is continuously differentiable. Continuously differentiable at p, all right? And this Jacobian of f inverse exists, then an inverse for f exists near p. The simplest version of this theorem is just calculus 1. When can you find an inverse to a function in you know, from R to R? If the function, if you try to find the inverse for a function right here, what's the problem? What we say about the slope of the tangent line right there, what? F prime of p equals to 0. So no matter how far you shrink in here, you can't shrink in far enough to find an open set around here where your function's injective, right? And you need the function to be injective close to the point if you're going to find an inverse. Now over here, on the other hand, if I'm here, right, if I go right there, if I just look close to the point, like here, let's say, right, then that part of the function passes the horizontal line test. And so if I call this I, f restricted to I is invertible. This is the idea of a local inverse. A local inverse is when you have a function which is not globally one-to-one, but you can take it and restrict the function such that the restriction of the function is one-to-one. You find the inverse there. This is a local inverse. Yeah.
Local and
It's not the inverse for the whole function. It's just the inverse for part of the function.
Local slash close to the points, as in there exists an open set, blah, 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 that kind of thing.
Yeah, yeah. So this up here is the inverse function theorem. It just simply says that invertibility of the Jacobian is a sufficient condition in the backdrop of continuous differentiability. If you take away the continuous differentiability, bad things happen. Let's not talk about it. So in the complex case, guess what? If the derivative in the complex case exists, then if you're close enough to the function, close enough to that point, you can find an inverse function for that complex function, and its complex derivative exists. All right, I have a careful proof in the notes, and I spent too long on this calculus 3 stuff today, so I don't have time for now. But let me look at its statement. Before I look at the statement, let's look at the calculation. So, for example, how about f of z equals to e to the z? Example 4, thank you. So, all right. Oh, I thought I saw somebody raise a hand, but it was just a trick of my eye. Oh, wait, nope. Okay, yeah. Is this function 1-to-1? In other words, if I have e to the z1 equal e to the z2, do you get z1 equals z2? We do not, right? We get that z1 is equal to z2 plus some 2 pi multiple of the imaginary number, right? 2 pi integer multiple. So in order to make this 1-to-1, I have to do what? I have to basically restrict, right? I have to restrict to some kind of strip that's like not more than 2 pi. It can't be more than 2 pi, right? Because otherwise then this function's not injective on that strip. So for example, if we have e to the z equals to w, we can say that log of w is equal to z, provided what? What do we need about w in that case?
The imaginary component between negative pi excluded and pi included.
The imaginary, okay, yeah, the imaginary part of w is, you said bigger than minus pi to this, right? Yeah. But can we do that if we want it to be differentiable in the complex sense? We can't because of the issue I was talking about earlier. We have the angle jump. So if we want it to be, you know, if we want the complex derivative, if we want this to be holomorphic, I have to throw out the equals here. In other words, this is true for w in the so-called deleted complex plane.
That's a branch cut.
Yeah. So you got to make a branch cut. So this is the idea of the branch cut. The branch cut the branch cut corresponds to a restriction in the domain to make the branch that you cut out the inverse for that restriction. Yes, sir.
So we're using the principal log there?
Yes. It's a choice.
Okay, so we can use either the regular log or the principal log to invert e to the z?
Well, we could say that. I mean, it would also be true that the alpha log of w would be equal to z from this equation. Like I can go like that. I could take the log alpha of both sides. Okay. But that would only be true. This would only be true given that w only if what? If the oh goodness gracious! Now I'm going to have to remember how I define this stupid thing. I guess alpha is less than the imaginary part of goodness gracious, not the imaginary part, the argument, right? Oh, rats. Ah.